Yes, awesome. All right. Well, hello, everyone. Welcome to February 2025 Link Tech Talk. My name is Colin Ryan Chandler, and our co-host is Mi Dai. We're both Link Frameworks product scientists. I'm at the Dirac Institute, University of Washington, and Mi's at the University of Pittsburgh. Link Tech Talks include presentations and demonstrations that showcase work done within the broader Rubin software and archives community with the goal of further enabling LSST science. And unlike traditional tech talks or other talks you might hear at a conference, tech talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analyses of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific time. So today we're fortunate to be joined by Francois Vanus, who will present One Network to Rule Them All, Multi-Modal Foundational Models for Survey Astronomy. Francois is a permanent research scientist at the CNRC in France, of the CA Paris-Saclay Institute there. Francois is also a guest researcher at the Flatiron Institute in New York, where he's a member of the polymathic AI team. He received his PhD in cosmology and inverse problems in 2015 in Paris, developed interdisciplinary expertise in deep learning for cosmology as a postdoctoral researcher at Carnegie Mellon and at UC Berkeley. He's now working on scientific applications of state-of-the-art deep learning techniques, combining concept of Bayesian inference, deep neural networks, and physical forward modeling. For the talk, please ask questions in Zoom on the hashtag LinkTechTalks channel. On Zoom, you can type questions in chat or raise your hand. Please keep the questions for the end if you can. And a friendly reminder that these talks are being recorded and they will be posted on our YouTube channel at a later date. So with that, Francois, take it away.
Right. Thank you very much for the introduction and for the invitation. Today, I'm very excited to tell you about some of the recent work that I've been doing with my team and some of the new methodologies that I think will be very useful for analyzing large surveys like LSST. So this talk is a way to introduce those methodologies and hopefully to start a longer discussion on how we can bring them to the Rubin community and our software environments. So the starting point that I want to take here is by stating a number of facts. And fact number one is the fact that over the last few years, starting in around 2015 or 2016, we've seen an explosion of the number of papers using deep learning or CNNs or neural networks in the AstroPH archive. So that, I think we are all aware of it. But one thing that may not be so obvious is that the vast majority of these papers have relied on what's called supervised learning. And in general, they have always been networks that have been trained from scratch to solve a particular task. So one of the side effects of this is that once a model has been developed, it's used once and then disappears and not reused by the community at all. So there is a lot of wasted time in all of this research. So just to show you a few concrete examples of the limits of this traditional approach, the first one is that in many cases, we're actually limited by the amount of supervised training data that we have access to for specifying a task. So the first example would be if I'm interested in developing some sort of neural network model to identify those rare strong lenses that you see here. I'm fundamentally limited by the fact that we only know a few hundreds or thousands of those. So it's not enough to train a large neural network. And then another situation where we are quickly limited by training data is something that has gained a lot of popularity in recent years, simulation-based inference, where you train a neural network to essentially estimate some physical parameters of the object that you're interested in. This is an example of a paper where we did it to find parameters of this microlensing event. But one of the issues that happens here is that to extract information from the signal, you have to train potentially a large neural network. And usually this requires a large set of simulations just to train this feature extraction network. And so that, again, can be fairly costly when the system is complex. So that means, these things are costly, but as I said, there's also limited reusability. Very often, when a paper has developed a model, that model kind of disappears and nobody reuses it. There is only very few exceptions to that rule. Like, for example, the ZooBot model developed by Mike Wamsey is an exception of that. But by and large, there is no reusability in any of this. And this puts very practical limits to the ease and adoption of deep learning for analysis and discovery. Every time that you want to use deep learning for your science, it's going to take several PhD months, even potentially several PhD years, before you can actually get to the point where you get your analysis results. All right. So that's the state of things in our field, but what's happening outside of our field, and in particular in computer science. So in recent years, in computer science, we have seen the adoption of what's called the foundation model paradigm. So if you ask 10 different people, they will give you 10 different definitions of what that means. But here is my understanding of what a foundation model is. So the first point is that you are going to try to build a machine learning model that is pre-trained on a vast amount of training data that comes from everywhere you can get your hands on the data. But not for accomplishing any specific task. It's trained on the data at large in a kind of task agnostic way. So if you want to get a very concrete picture of what it might look like, if I want to train a model on images, for instance, the task that you would use is you provide patches of an input image, and you ask this model to predict the missing patches of that image. So this is not specific to any sort of downstream use of that network, but it turns out that this particular task is actually complex enough that it will force this encoder network that you have here to learn a very deep and meaningful representation of the data that you can then leverage in a second step in an adaptation phase to adapt your model for some particular task that you want to do downstream. And then the final piece of what a foundation model is that in practice, you can also combine those foundation models together to build more complex systems that can do more challenging things. So that's the first point. The second point is that because now we're no longer trying to train models specifically to solve a particular task, it also means that we can use a lot more training data, even when we don't have access to labels for that training data. So that is kind of illustrated here on this plot. What you see here on the left is several generations of supervised models for the ImageNet classification problem. And so this is just a matter of giving you a cat or dog picture, tell me if it's a cat or a dog. You can see that over time, architectures have improved, accuracy of these models have improved, but it has kind of saturated because there was just a finite amount of existing image data with labels associated to it, and you couldn't reach any better accuracy than this, given that training data. But now, with this kind of foundation model approach, I can have much larger models that are trained on billions of images. Most of these images, I don't know what the label is for them, but then I can very efficiently adapt them once they're trained to this classification task. And because now I have more training data, I can go to larger models, and you can see that I'm more able to saturate that that particular task. So I get more performance, and I can train larger models. And the final, let's say, piece of information that I want to convey is that this adaptation phase can be very easy. And to convey that, I will mention this idea of linearly accessible information. So one thing to keep in mind is that these pre-trained models, they can be very large. In many cases, you can extract from them some sort of embedding of the input data. And so that embedding, you can think of it, for instance, as a vector of dimensionality D. D is usually pretty large, from 512 to 2000. And then those embeddings can be very easily turned into a predictor for any type of prediction task you're interested in. So the simplest way of building a predictor is called linear probing. So once you get the embedding from your data, you just train a projection matrix that will go from this embedding dimension to, for instance, here for a classification problem, the number of classes that you're interested in classifying. And then with very few examples, you're able to build very performant classifiers by just training this essentially linear projection on top of the embedding. So here you can see that with as little as 10 examples per class, you can already saturate the classification accuracy by using a large pre-trained model. So the main point is that adaptation of those large models is very easy as a linear layer, and you can reach state-of-the-art performance. All right, so what would this mean for us in practice, astronomers? Well, the first point is that if this is true, I never need to retrain my own neural network from scratch. I can use a pre-trained model, and with a simple adaptation like a linear matrix, I am almost guaranteed to be as good as I possibly could for any task that I want to do. The second point is that because this adaptation phase only requires a few number of examples, now it makes it practical to use deep learning for things that have been traditionally difficult, like finding really rare objects in a survey like a Euclid or SST. And then the final point is that since this information is so accessible in an embedding space, I can use very simple analysis tools in practice for any downstream analysis task. So concretely, that means that if I have access to those embeddings, I could, with just 2 lines of scikit-learn, turn those embeddings into a predictor for a particular property that I'm interested in, with no deep learning involved at that point, and still reach state-of-the-art performance. So that really changes the way that I can, analyze my data and makes it a lot simpler. And so that's the sales pitch, but now let's see if we can actually make it happen for our use cases. So the first step in transitioning from like the high-level idea and wish list to an actual application is data. And so our first effort in that direction is something that we call the multimodal universe, which is the first very large-scale set of astronomical data that has been compiled specifically for the purpose of training those large foundation models. And so overall, this represents over 100 terabytes of data that is ML ready. And I'm going to tell you exactly what that means. All right, so the first thing to realize is that those very large foundation models trained by Google or others rely on extremely large data sets. So for instance, that usually referred to as web scale data sets. So for instance, one of those data sets is this Leon 5B data set of image and text, and that is more than 2 billion pairs of images and data and text. So you might think, okay, well, in astronomy, we do generate a lot of data, so what's the problem? That's true, but as you may already realize, most of the data that we do have access to is not stored in any sort of structured and ML-friendly way. So if I want to do machine learning with images, for instance, with current generation of models, we need to have access to postage stamps, and there is very often not just a widely available collection of postage stamps. And then the second point is that even if I know how to access data and extract postage stamp for a survey, different surveys store data differently and not consistently. And so it's not very easy to train jointly from, let's say, DES imaging and HSC imaging. And that requires, at the end of the day, significant expertise for each data set. And those are factors that prevent or have prevented so far the extension of large-scale training data. So what we did to go and solve this problem is assemble a team and a project that we call this multimodal universe, with essentially the idea of bringing together astronomers with expertise in different data sets, such that we could work together to standardize the conventions for storing and accessing this data in some very ML-friendly way, and in particular through Hugging Face datasets, which is kind of the convention and state-of-the-art out there for storing and accessing data for training neural networks. And one of the important factors here is that we want to target large astronomical surveys with many different types of instruments, and they should also cover many different types of astrophysics downstream use cases. So among the different types of data that we have collected, we have imaging data from the legacy surveys here. We have JWST data, we have time series, hyperspectral images, and a lot more. But perhaps the most interesting point for this audience and for this talk is how do we go about gathering all this data from different surveys turning them into a consistent format without requiring a lot of time from the expert that know how to access this data. So the strategy that we use here in this multimodal universe project is to only ask the scientists to provide one thing that we call those download scripts. So those download scripts is just a Python script that describes how I can query data from a particular survey and turn it into a standardized HDF5 format. And so that is usually something that is, fairly approachable for someone that is not a software engineer, but that has expertise on each of these surveys. And so once people have provided this, we can run all of those scripts in a centralized location, and that has happened for version 1 of the data at Flatiron Institute. And then we can bring a single repo with all of the data compiled in a consistent format and accessible through this Hugging Face dataset format. Once the data is in one place, we also provide utilities that allow you to cross-match different datasets, different surveys, and that is a key factor that allows you to build this modality, this multimodality aspect that will be very important in the rest of the talk. For a given instance, you can extract all the information associated to that instance, and so you can get the same object seen through HSC through other surveys from DESI or whatever. And so how do we kind of standardize the data format? We only ask very little things to try to keep it very simple. The first thing is that every standardized data should provide us with an object ID and some array deck. That's all we are asking for. But then we ask for modalities of a given type. So for instance, images to provide a few additional metadata. So for instance, an image should always provide a flux, an inverse variance field, a band key that tells us which band this frame is coming from, some information about the PSF, and some information about the pixel scale. So this is not, all the possible information you could collect about an image, but this is a fairly condensed way of representing your image and something that you can define no matter what your image has been taken from. And so that allows us to standardize in a very simple manner, all images into just one format, all spectrum in one format, no matter where the spectrum comes from, and same thing for time series. And then the final piece here is that to make the cross-matching pretty efficient, we also have a strategy to store the data in HILPix regions, which then allows us at inference time, or when we try to extract batches of data from the survey, from the MMU, we just go through HILPix regions and then cross-match within HILPix regions based on array deck, and that is really fast and can be done live as we feed the data to the neural network that we want to train. Just quickly flashing the data set that we have aggregated in this version of the data set. There's too many to look at, but let's say we have significant fraction of the sky seen through the legacy survey, which includes all of DES imaging. We have all of HSC, PDR3 imaging, for instance, but we also have all of SDSS and DESI spectra as well. We also have Gaia and a bunch of other surveys. All right, and so the last point I want to make is that once this exists, it makes it trivial for anyone to get started training any machine learning model on the data that has been aggregated and standardized through this MMU. So for instance here, this is actually not an MMU utility or library. This is the Hugging Face library that you can install, and you can import this utility. And then in 2 lines of code, you can stream legacy survey imaging directly from the Hugging Face hub. You can see that this example will follow the convention that we have adopted. So this image, if it's actually a dictionary, and if we look in the dictionary, it will define a flux, it will define the bands that correspond to each stuff like that, and the PSF information as well. In addition to that, we have additional fields like the flux measured as part of the pipeline. And all of that is trivially accessible. All right, so now that we have solved the first hurdle, we have vast amounts of data available. The second point is that the data, although it has been formatted in kind of a uniform way, it's still very diverse. We have spectra, we have images, they have different pixel scales, they have different sizes and such. And so the new problem that we're confronted with is that how to have a neural network that can deal with all of that diversity of data. And what we would like to have access to is what I would call a universal model, something that can act on all of that data jointly. So if we think about this, you can think about two different approaches. On the one hand of the spectrum, you could imagine having one model for every type of imaging or every type of modality. So I have a spectrum model, I have an image model. And that has been, up to very recently, the way that we have thought about this problem in the community. So for instance, I have a paper from a few years ago developing models that know how to handle images. Peter Melchior and his team in Princeton have developed similar things for spectra, but until very recently, there was no crosstalk between this type of model. They were talking very much, they were very much on their own. But now if we allow ourselves to dream and think about the future, the thing that I would really like to have is just one neural network that potentially can work at the byte level representation of my data. So directly at the lowest common denominator of any data that I have. So that is still a bit far out in the future, but there are still already papers that are trying to do this. And this is an example of a paper that have very good performance at image classification, working with a transformer directly from the byte level representation of the data. And in the case of images, this will work. So you could imagine that in the future, this is where we will be. And this is all broken. But what I want to show you now is two different approaches for trying to bridge that gap between different modalities and data type. And the first one I will tell you is about this Astroclip paper that we released last year. So here, the idea is to do cross-modal pre-training, and I'm going to explain what this means. And this is a paper that's available in MNRAS, and that was presented at a workshop in RIPS last year. So first of all, what is CLIP? So CLIP, we didn't come up with it. It's a pretty standard strategy, but it's one that has gained a lot of popularity by work by OpenAI from a few years ago. And it stands for Contrastive Language Image Pre-training. So the idea here is that we want a way of training an image encoder or text encoder with what's usually called as a weak supervision strategy. So we're not training this image encoder for solving any particular task, but the thing that we're going to ask is that once the system is trained, the output of the image encoder should align very well with the output of the text encoder if the text and image correspond to the same scene. So they should align in the sense of the vectors that are output of this model should be aligned with each other. And when the two examples here are not related to each other, they should be misaligned. And that's what this loss function here is trying to promote. So this you can do at scale as long as you have association between data, input data and output data. And what is pretty cool is that once this model is trained, you can directly use it out of the box without any additional machine learning coming up for building downstream applications. So here is an example of using this trained model for doing an image classifier. What you would do is that you take the image, you encode it into the output of this model, and then you take a bunch of sentences saying this is a picture of a cat or a dog or a car or whatever. And then you just look at which of those sentences will align the best with the image thing that you have. And boom, you have a classifier for this image. This is something that's usually called zero-shot prediction. And it's a first level illustration of the fact that you can leverage those pre-trained models for downstream applications very, very easily. All right, so we took this idea and we transposed it to the astronomy world by replacing essentially text by the language of stars, which are spectra. And we apply exactly the same strategy. So we have here a pretty large scale image encoder. It's a transformer model. I can tell you more about this afterwards if you're interested in. We, in the same way, have a neural network that can encode spectra. And then we train them such that when the image and the spectrum correspond to the same object, they should align very well in that embedding space, and otherwise it should be misaligned. Once you've built this model, to first order, you can use it for doing things like similarity searches. So you can think of this as being able to transform from your data space to this embedding space. And one thing you can do is to look for neighbors in that embedding space. So here is an example of that. I take this image, I embed it into the space, and I look for all the closest neighbors of that image in that space. And this is what I retrieve. So the interesting thing is that it looks similar, but these will also be objects that are very similar physical properties. And based on that, you can, off the box, out of the shelf, start to build, prediction models. And so, for instance, if I want to build a redshift estimator or a stellar mass estimator, I will just look for the embedding of a spectrum for which I can extract the redshift or the stellar mass of the subject that is the closest to my image. And this I can do with, again, no machine learning involved. It's just a nearest neighbor search, and I can get an estimator from that. And then you may ask me, well, is that a good estimator? Is that a bad estimator? And the answer is that it's a good estimator, and I'm going to show you what I mean by that. So here is the result of doing redshift prediction if all I have access to is the photometry of an object. And this is this is a little bit garbled, but this is redshift prediction if I can train a supervised machine learning model from the images. And if you look closely, you can see that the supervised model is tighter around the one-to-one line, which means that there is more information in the images than in just the photometry, and the model has been able to extract that. But this is still a pretty large model, trained from scratch specifically for that case. But what we can do is instead use our Astroclip model that you have here on the left and ask the same task, trying to take the embedding that come out of this model from the image and try to predict redshift by just looking k-nearest neighbor regression. So again, there's no training involved here. It's nearest neighbor regression done with scikit-learn, nothing else, on the already computed embeddings that come out of the model, and you reach better accuracy than a supervised deep learning model that was trained specifically for that. All right, so I'm going to skip the reasons why this works, and I'm very happy to go to that after. I'm going to skip some of the methodology that goes into making this happen in practice. If you're interested in this, ask me questions afterwards. But I want to finish the big picture talk first. So that's the first approach that we developed more than a year ago. But one of the things that you may have noticed is that this was still reliant on having two different networks that we taught to align to each other. And the new version of things that we're currently developing that we call Aion is going further and is trying to bring the machine learning model closer to the data and doing this fusion, having fusion of different modalities happening earlier than is done in this previous CLIP model. All right, so what does that mean? So before I dive in, I want to say that the thing that I'm going to tell you about is something that we've been working on with a very large number of people for almost a year now, and we're very excited to be able to share the first results, and the full model will be available pretty soon. All right, so the first question is, what will make Francois happy? So Francois has been working on deep learning for almost 10 years now, and is very specific on what will make him happy. So the first thing is that he would, in principle, like to have access to a model that he can use on any input data type that he wants to operate on without having to worry. And so what that means is that if you give me an image or a spectrum, I don't want to have to think about the type of network I need to apply to this particular data type. I can use one thing, and that one thing will work well, right? And then the second thing that will make Francois happy is that if this one thing that can operate on any type of data without training it specifically, for instance, to extract physical information, physical parameters from galaxies or spectra, I want my model to just to have looked at a lot of data and have discovered by itself that there is physical information, that there is structure, and I can extract that information very easily for downstream applications. All right, so let's see if we can make this guy happy. So the first question towards that goal is assembling data. So in our Aion 1 project, we started by getting our hands on a vast amount of postage stamps that come from the multimodal universe. And overall, we have aggregated about 120 million multi-band galaxy images from the legacy survey. So this is mostly coming from DES. And the only thing that we have done to the raw data is just selecting for extended sources, asking for full color, and applying a magnitude cut. Now, because DS is nice, but HSC is nicer, if you ask, depending on who you ask, we also wanted to complexify the problem and have access to a different set of images. And so we included HSC wide from the PDR3. And again, similar cuts, but now we have more bands in the HSC data. And as you probably know, the pixel scale is also going to be different. The depth is going to be different in those images. But images is nice. We want more than this. So we included also DAISY early data release. We included the 1% survey. So here we took everything, no cuts applied. And we also gathered all of the SDSS data. Again, no cuts applied apart from primary targets and no flagrant flags, data quality flag. And we also wanted to experiment with more diverse data. So we included Gaia, the latest data release from Gaia, which mostly gives us access to low resolution spectra, but we also have flux measurements and parallax measurements coming out of the satellite. All right, so that's a lot of data. But now the problem is, how do I gather all of that data into one model? So the first step in reaching that goal is data standardization through what we call tokenization. And it's called tokenization because it comes from what happens in language models that Google, OpenAI, and friends are developing these days. So the idea here is I want a mechanism that I can apply on any type of data that I'm working with that will go from the raw pixel level data to a representation that we're going to call tokens. And a token here is just going to be a number. So this is just a sketch, but the idea is that I can turn an image to a set of 9 tokens here in this sketch. And those are just 9 numbers. And then I have a process also, if I want to decode those 9 numbers back into an image. So the way that we do this in practice is by training those autoencoders. So themselves, they are networks. They are specific to a particular class of modality. So we have a specific image encoder-decoder system. And the way that this is trained is by minimizing the reconstruction loss. So I want my input image to be modeled as well as possible by the autoencoding. This is the encoder network, the decoder network. And we also introduce this discretization step at the bottleneck here to turn the bottleneck into discrete numbers. So very happy to talk more about the details of different discretization step. We use something that's called FSQ, which is very easy to implement and is essentially just approximating the numbers to their closest point on a regular grid. And that works really well. But one of the considerations that you may have here is that, okay, remember that I use HSC and DES images, they have a different number of bands. They also have different numbers of properties. So what I would like to have is a single tokenizer image model that can handle that amount of complexity. And so the strategy that we use in practice is something that comes out of other work that was developed by Polymathic. And essentially, the idea is that if I have different fields, here it was for some fluid dynamics problem, but the same thing for us would apply for different bands here. We have a way of identifying which band I'm looking at and embedding it at the input of this model with a band-specific filter, band-specific parameter. And then we're flexible to having more or less bands and to the type of band that we're inputting at the input of the model. So for instance, a single model, this input layer will allow us to embed HSC bands or DES bands, and the model will know that it's actually a DES band or an HSC band, and we also encapsulate that way information about the pixel scale in that input image. And so with that, with this combination of schemes, we can have a single model that can act on any astronomical image as long as we knew ahead of time to account for that particular band. And then we applied essentially the same mechanism to more than just images. We did the same thing for spectra. We did it for things like segmentation maps, so not just pure data modalities, but fields that we may be interested in asking of the model or providing to the model, and also for a limited number of physical parameters. So we included, for instance, redshift as one type of modality that we can tokenize, but we also have absorption, galactic extinction, and flux measurements and such. A bunch of what we call scalars we can also include in the same principle. And overall, we have 39 different modalities that the model is able to understand, and that's why we call it omni-modal. All right, so once we have solved this problem, we now have a way of making all of this diverse type of data homogeneous. So what we want now is to train this model such that it understands, for instance, that a given spectrum corresponds to a given image. And so the way that we do this is by identifying pairs of data across pairs of surveys. So for instance, we build like joint examples of imaging data with spectral data. And you have here the number of such examples that exist and that we can account for. So once we have those pairs of examples, we can feed as an input to our model a subset of tokens for a given modality. So for instance, here in this illustration, we would provide a subset of those image tokens, also a subset of these spectral tokens, and any other inputs that we have available for that particular instance, for that particular object. And then what is very interesting with the type of model that we're using is that we can request particular outputs of the model. The outputs are not pre-built. It's not always outputting the same thing. And the way that we do this is that this decoder here can take as an input a token, an empty token, that specify what output I'm asking. So here we are saying, okay, I've given you a bunch of those image tokens, and now I'm asking you to predict all the remaining ones. Or I could ask you to predict the spectrum that corresponds to that image. So that is one of the key features of these transformer models, is that they're completely flexible to any combination of input and output data that you may want. And in practice, we train it over randomly sampling some set of input tokens and asking for some set of output tokens. And if you think about it, it actually means that this model that we have here is trained to learn all the joint and all the conditional distribution that exist between the data types that we have provided. I should also add that this is a generative model. So this is Gen AI, if you want to call it that way. We can provide, for instance, here nothing and ask image tokens at the output. This will generate images out of the blue. We can provide flux measurements here and ask for an image at the output, and that will provide an image that have the flux that was provided as an input. So it's very flexible. And so the last point between now and the results is being able to train these models. And these are not cheap. So we were very lucky to be selected as part of a grand challenge that was organized on this Jean Zay machine that is sitting near Paris in France, which was extended last summer to a new partition of 1,400 H100 GPUs. And so we used this challenge to train several versions of the model, going from 300 million parameters all the way to 3 billion parameters. And what you can see, which is just a loss function during training, over time, you see it goes down, but you can also see that it goes down as we go towards larger and larger models significantly. All right, so going to the results now. So just to show you some of out-of-the-box capabilities, this is not necessarily what we're going to use for science, but it is cool to see what this model has understood of the data. What I'm showing you on the left is an illustration of what I will call survey translation. So I'm asking the model to generate an HSC image given a DES image. And you can see that it's kind of zooming in. It's because the pixel scale is different in HSC and DES. And so this gets, magnified because we're zooming in into this image. And the details are being added by the model because they are not necessarily present in the input image. And then on the right, I want to show you another example of this, but this time on spectrum. We're asking for a DESI spectrum given a Gaia low resolution spectrum. So for people that know about Gaia, what we actually provide are the XP spectrum coefficients, not an actual line, but a bunch of coefficients. And we're asking the model to generate plausible DESI spectra that correspond to this. So you can see, for instance, if I look at this particular line, that the Gaia spectrum in red, because it's a low resolution spectrum, it doesn't show any line here, but the model has seen enough stars in DESI and SDSS to know that for this particular low resolution spectrum, there should be some line here, and it's putting them there. And you can see in blue, those are several samples, generated samples out of the model, and the dark line is the truth that is known in this case from the DESI instrument. You can do other things as well. We train the model specifically to understand redshift. This is the only physical parameter that we included during pre-training of the model. And I apologize, this is in French, but it should be fairly straightforward to understand. This is an illustration of asking the model to predict the redshift of this central object here by giving it the image or just giving it the photometry. So if I just give it the photometry, it's going to give me this red line that you see here. It's pretty broad. The interesting thing that you wouldn't see it here, but those neighboring objects are actually located around this redshift. So what this probably means is that the photometry is blended and the model is just predicting a very broad and blended redshift. But if I provide the image, I get a much tighter prediction, which is this orange one. It's closer to the truth. All right. I will skip a little bit of this. The cool thing, the main takeaway is that it understands how to translate between data types, even when it's not specifically trained for that. This is just an illustration of asking the model to generate galaxy spectra, given an image of a red and a blue galaxy, in cases that it has never seen during pre-training. So for instance, we never show it this spectrum along with an HSC image, and it's still able to do this task. So that shows that the model really understands what's going on in data. It's not just simply replicating what it has seen during pre-training. All right. And so to finish, now comes the real interesting point for us is how do we use these methods for accelerating the science that we can do downstream of this? And so to begin here, I want to take you through a little journey of how conventional scientific workflows have used deep learning. And here are two conventional scientists from like almost 10 years ago. And the way that they used deep learning at the time was going through the following steps. So first step, you spend a lot of time building a large-scale training set for your model that is as close, realistic to real data as possible. Then you spend a lot of time designing a neural network architecture specifically for your data that you are looking at. You have to deal with lots of data preprocessing and normalization issues. Then you need to train your network on some GPUs for like a day or so. It takes time. It fails a lot. You have to train it several times. Then you apply it to your particular problem. You get some results. But at the end, you throw it away because your network was very completely specifically made for your particular data, and they would not be able to use by anyone else for any other purposes. And so now, changing the way that we do things, if I use a foundational model approach, everything that has to do with this pre-training, understanding the data essentially, has already been taken care of. So if I want to adapt this model for a new task, all I need to do is to come up with a small training set that will associate example of data and example of outputs that I want to get. And then, as we'll see in a minute, I can adapt an existing model in a matter of minutes, if not seconds, and I can get state-of-the-art results. And so that is really transformative in the speed at which you can get, the analysis that you want to get. There are different ways that you can do this adaptation phase that is illustrated here in this diagram. What I'm going to show you now is just one of those ways, but the simplest one, and the one that will get you very good results in the minimum amount of time. essentially embedding-based adaptation. So showing you how you would do this with a model like Astroclip. So remember, Astroclip was our first generation model. It only works on images and spectra and only works on specific images and spectra. But the cool thing is that it's a frozen model, and I can use it without having to adapt it or fine-tune it. So in a workflow, in a scientific workflow, the way that we use such a model is the following. I can import from scikit-learn a k-nearest neighbor regressor. I can query or I can apply the model either online, potentially through an online API or locally, it doesn't really matter, on my images. And then 2 lines of scikit-learn, I get the best possible result. And this is examples of this 0-shot line here. It's actually just exactly doing this. And will get you the best result on predicting, for instance, stellar mass or the age or star formation rate of galaxies, much better or comparatively better to a supervised dedicated ResNet model. All right, so no local GPUs is needed here, potentially. And the embeddings, they can be pre-computed even as part of the survey processing. So you could imagine that in the future, Rubin would include those embeddings as one entry in the catalog, and then I can achieve state-of-the-art results better than if I had access to the pixels themselves directly in 2 lines of code from those embeddings. All right. And then to finish now, how we would do this with Aion, well, it's an encoder-decoder architecture. So the cool thing is that you can use it just as an encoder that is flexible to any combination of inputs you have. So if I have images and spectra or photometry, I can put all the information that I have about an object in, and I get some embeddings at the output of the model. And so then from these embeddings, so here, everything is frozen. There's no training involved at inference time. And I can use them in very simple fashion. So the simplest way I can use them is by what's so-called mean pooling. So I do the average of these vectors here, and I train just a linear projection matrix, and that will give me a predictor for something. Or I can do what's called attentive pooling. It's just an attention layer, but again, it's a very simple thing that is added on top of those embeddings. And then the way that it would look like in an API would be something like this. I have some input data. I tokenize it to make it uniform. And as long as it's something that the model knows how to understand, like HSC images, I'm good. And then in 2 lines of code, I can build one of those adaptation layers, which again is essentially just a couple of matrices to fit by doing just a fit and predict thing. And boom, I have a predictor for whatever I want to do. And in the last few seconds, I'm going to show you examples of this. Let's say that I want to build a morphology classifier with just a few examples of different types of data. For instance, BARD or edge on galaxies. Here is how well the accuracy of just a single linear layer, so it's taking the output of this model and training this M matrix, will look like as the function of the number of training set size of the training set that I have. And the solid line here is what happens if I try to train a model from scratch with a CNN for this particular task with that budget of data. And you can see that this simple adaptation layer gets you very close to optimal and saturates very quickly. And it gets better as you go towards larger embedding models. But you can do more complicated things. I can do the same thing now to try, for instance, to predict segmentation maps out of my embeddings, again, with just a linear prediction layer. It works the same way. And I can also do the same thing for estimating physical properties of my objects. For instance, here, the redshift or the stellar mass or the edge or whatever I want. And again, it scales faster and better, it saturates faster than a supervised baseline that would be built specifically on images. And I will conclude on what I think is the coolest application of them all with this single model, is that I can do what's called example-based retrieval. So here, what I do is that I take, for instance, this image that you see on the left, I feed it to the model, I take those latent embeddings, and I average them. That gives me a vector. And I look for all of the other images that have vectors that align very well with this query here in my database. And here we're working with hundreds of thousands of examples. And the one that aligns the closest they will be objects of similar types. So if I'm looking for spiral galaxies that show those features here, this is what I get. If I'm looking for mergers, this is what I get. And if I'm looking for something that is a lot more rare, like a strong lens, something like this, I use that as my query. And the sixth example that I get will be a strong lens. And then I can keep going with this. This is from just a single query. If I have more, I can build a more specific classifier for finding those rare objects. All right, and I'm going to stop here with two opportunities to engage with the project if you think that's cool. The first one is that we'll announce next week a beta testers program where we'll encourage people to work with us to get advanced access to the code and to the model itself to try it out on a bunch of different use cases. And that will also help us refine the API that we want to provide the user. So if that's something that you would be interested in, please Slack me on the LSST DA Slack, and I will make sure to keep you notified as soon as the program is announced. And the final thing is that we are also hiring. If you are a postdoc or if you know some postdocs that are looking for jobs still, we have two positions open in Paris to work with the rest of the polymatic team, which involves also working at spending some time at CCA. And so feel free to look at the ad, but feel free to also reach out to me directly if you're interested in that. And I'm going to stop here. Thank you very much, and happy to take any questions.
Awesome. Thanks very much. I thought that was awesome. I'm still reeling from the 1400 H100s, but trying to get my focus back. Yeah, we do have some time for some questions. You can ask questions in Slack, chat here on Zoom, or raise your hand. I see we've got a couple of hands up already. Looks like the CME room. Go for it.
Hey, Francois. This was a very impressive work. Any plans for time domain for light curves?
Yeah, 100%. Yes, that's on V2, and we're gonna make it happen as soon as we can. We're already working on, let's say, stellar viability. That's what I will say. But one of the goals for the postdocs that we're advertising is to extend this to all of ZTF and preparing for SST time domain.
Sounds great. Thank you.
Thanks. Martin, go ahead.
Hi, can you hear me? Hi, Francois. It's Mariano from Corda. Very nice talk. I would like to ask you about, we are trying to use Astroclip for downstream tasks, but they are mostly dominated by low redshift galaxies. And in the new model, you mentioned that the combination of HSC data with DAISY data is out of distribution. What do you mean for that?
Right. So that's what I will call a happy accident. So one of the key, aspects of training this model is by showing it pairs of, let's say, images and spectra. That's how it understands the connection between the two. And so we build during training, we have pairs of legacy survey and DAISY, which you can see here through this line. We have also SDSS and DAISY, blah, blah, blah. But there is no direct connection between HSC and DAISY. That was a happy mistake, which allowed us to check that even though it was never trained specifically to predict a spectrum from an HSC image, a DAISY spectrum, it was trained to build an SDSS spectrum, but those are understood as two different modalities. It still works. And it shows that it actually discovers something deeper in the data than just surface level, just remembering to do the thing that it's been trained for.
Okay, because this probably is the most interesting part for Rubin, right? In order to make predictions before the data, right?
Yeah.
Also, just another question: what could be the effects of the blending of images on the embedding of this model? There's some consideration about or pre-selection of sources on this.
That's a good question. So the way that we select object is strictly based on those cuts plus some quality cuts. So some of the quality cuts may have to do with blending, maybe triggered in case of weird objects, but we don't specifically apply anything else than this. So it is what it is. And the goal is that you can then come in and take any postage stamps that you have and be able to apply it. So we don't want to apply specific cuts looking at specific galaxies or anything like this. We want to encompass everything up to some depths from the training surveys.
All right, thanks.
Thank you so much.
We have just time for maybe one more quick question. Sorry, we're running low on time, and I know our speaker has a hard deadline as well. Dirac Space, you were next in line.
So I will hold most of my questions, Francois, for when you come and visit us next month. But let me just ask one. So regarding these out of distribution results, essentially when you give it an image and it tries to predict the spectra and all these things, right? So for these kinds of tasks, you know, one of the general risks of, let's say, using any traditional machine learning model is that it predicts to the average, like in the sense that if I see a blue galaxy, it must be a disk galaxy. That's the average prediction which comes out. Given that these models have more contextual knowledge and especially this multimodality aspect, have you done some specific checking against baseline ML models on whether it is doing better or worse in that respect?
So we have not, and I have two answers to this. The first answer, and that it is a great question, and this is exactly why we want to open this beta testers program, because there are tons of questions like this that are super interesting to explore, and we think it will help, you know, build a better picture of the model and even potentially catch some issues before we make it widely available. So if you're interested in that question, we'd love to work with you more directly on that. But the second answer that I will have is that we tested specifically this sort of transfer across different surveys. So here is, for instance, the result of training this adaptation layer for classification of morphology. We train it on legacy survey images, and we apply the same layer directly on HSC. And that is not something that I thought would work at all, because typically you don't expect machine learning to transfer this way. But you see that the accuracy is very close to the original one. And so this doesn't have to be, but it is a sign that something deeper is happening.
Great. Thanks very much, Francois. Sorry, Stephanie, Max, Michael. If you wouldn't mind maybe slacking Francois on LSSTDA Slack, that'd be awesome. Again, let's thank Francois for the fascinating talk, and thanks to everyone for attending Link Tech Talk series today. Our next Tech Talk will be on March 13th, where we'll be joined by George Beckett at the University of Edinburgh. I'm going to talk to us about the United Kingdom International Data Access Center, or IDAC, and getting ready for LSST Data Release 1. We hope you will join us then. In the interim, please join the LSST hashtag Link Tech Talks channel on Slack on LSSTDA. The link LINCC at lists.lsst.org mailing list for more information and future announcements. There is much more information on our website there at the LSST Discovery Alliance. And we will post today's talk on YouTube in the near future. So thanks again very much, and have a great rest of your day. Thank you.
Thank you, everyone.